Welcome dear student, how are you and how your study is going on? So today we shall learn about a new topics of nuclear physics which is very interesting and has a lot of application in nucleus and in our daily life. Okay, so in the previous day we shall talk about the nuclear mass effect, binding energy and the what is radioactivity, how radioactivity is discovered. If you not know, please go to my channel Talking Physics with P.R. Sarkar and search for it. Okay. So today we shall go with a new interesting topic which is the radioactive decay law, which is about the radioactive decay law. Radioactive decay law. Radioactive decay law. According to Soddy and Rutherford, the radioactivity is a process. Radioactivity is a process of in which the nuclei is unstable and it emits alpha, beta or gamma rays. Number 2 is radioactivity, that radioactive or the phenomena of radioactivity is random process. That is, we cannot predict which nuclei decays first or which nuclei decays last. It is a matter of chance and it is spontaneous. Number 3, it is a spontaneous process. It is a spontaneous process and it does not depend on the physical. It does not depends on physical or chemical condition That is, the radioactivity cannot be accelerated, cannot be retarded, cannot be stopped, cannot be initiated. It is totally a spontaneous phenomena. So on the basis of this, we can go with radioactive decay law. So it is impossible to tell that for a particular nuclei that if it's decay or not, but there is a probability, there is a matter of probability that if we take a bunch of nucleus, then it has a probability that it becomes decay or disintegrate. So the radioactive decay law is basically gives a relation between the decayed and undecayed nuclei. Suppose there is n number of nuclei, n0 number of nuclei. N0 is the number of radioactive nuclei at T is equal to 0. That is, initially the number of nuclei present in a radioactive sample is N0. After time T, n number of radioactive nuclei present in that sample, that is, the number of undecayed nuclei is n. So n is number of undecayed nuclei present after time T. So according to radioactive decay law, the rate of disintegration that is the rate of disintegration, which is dn dt, is proportional to number of undecayed nuclei. This is known as radioactive decay law. This is known as radioactive decay law. I know you all know this. All you know the radioactive decay law. But can you tell me the significance of radioactive decay law? What is its importance in nuclear physics? Okay. So, in this chapter, we cannot go or cannot know about the radioactive decay law, but we shall also know what is the importance, that why we shall learn this law, why we shall know this law. So, let us give a look here. We can go with the derivation, but at first we shall go with the statement. That is, what is radioactive decay law? That is the number of radioactive nuclei disintegration, that is decay, disintegration, number of radioactive nuclei disintegrate, not disintegration, disintegrate per second of a sample at any instant is directly proportional to number of undecayed nuclei in the sample at that instant. This is the statement of radioactive decay law. The number of radioactive nuclei disintegrate per second, that is dn dt, is directly proportional to the number of undecayed nuclei present in the sample. So, here consider that here is no initial number of nuclei involved. That is, we cannot involve here the term n0. Rather, if we go with the derivation, we can go with the value of n0, but in the statement, the n0 is not included. So, we can write it dn dt must be equal to minus lambda n. Lambda is a constant which is called decay constant or disintegration constant, and negative sign indicates that while the time elapsed, the value of n decreases with time, because more and more time elapses, more and more time goes, more and more radioactive nuclei disintegrate, so the number of undecayed part is smaller, so the negative sign arises. Therefore, if we take dn by n equal to minus lambda t, take the integration on both sides, we can get log e n minus lambda t plus c. Take as equation number 1. Now, at t equal to 0, that is initially n equal to n0. Put t equal to 0 in equation 1, we can get this term 0, n equal to n0, that is log e n0, and c, we can get the value of c is log e n0. So now put the value of c in equation 1. We can get log e n is equal to minus lambda t plus log e n0, or log En minus log En0 is equal to minus lambda t. Minus lambda t. So, go from this to this step. Log A minus log B, that is log A by B. So, we can get log E base n by n0 minus lambda t, or n or n0 equal to e to the power minus lambda t, or n is equal to n0 e to the power minus lambda t. This is the mathematical derivation of decay's law, radioactive decay law. N is equal to n0 e to the power minus lambda t. Now, what we can know from this equation? What we can know from this equation? Please note down in your copy so that you can understand in later, or if you understand then you can read it from any textbook. Okay, so I can just erase it for the time being. So we shall go that n equal to n0 e to the power minus lambda t. So from this we can conclude, what we can conclude? We can conclude that number one, as this is exponentially decreased, that is the decrease of radioactive nuclei radioactive nuclei is initially very fast and then decrease with time. I shall draw the curve, exponentially decreasing curve. From this we can clear it. The decrease of radioactive nuclei is initially very fast, then with elapse of time the decrease rate is slow. Number two, larger the value of lambda, it will decay fast. Larger the value of lambda, it will decay fast. Number three, at t tends to infinity, n becomes n0 e to the power minus lambda into infinity, that is e to the power minus infinity is 0, we can get the value of n0 equal to 0. That is at infinite time, the number of radioactive nuclei or undecayed nuclei becomes 0, or the sample will becomes 0. Any number of samples becomes 0 at t equal to infinity. That is, the range of decay is very fast. That is, the range of decay lies from 10 to the power 10 years to 10 to the power minus 15 second. This is the range of decay. This is the 10 to the power 10 years is the age of our universe age. Okay. So some radioactive nuclei decays very fast and some radioactive nuclei decays very slow. So actually the half-life of radioactive nuclei lies between 10 to the power 10 years to only 10 to the power minus 15 second. We shall now draw the graph of radioactive decay law and try to understand the points we have just written. Sorry, we have just written. So, if we draw the graph, if we take a plot like this, take time along x-axis and along y-axis the value of n, that is the number of undecayed nuclei. So we can get 0 T half. T half is the half-life, the time at which any radioactive sample becomes half of its initial value. This is 2T half, that is the twice of half-life, 3T half and so on, and this is the value of N0. So at first, that is at T equal to 0, suppose this is T equal to 0, the value of N0 is, the value of radioactive sample is N0. At T equal to T half, the graph will be decreases exponentially. At T equal to T half, the value of N is becomes N0 by 2. And at time T equal to 2T half, the value of N0 becomes N0 by 4. And T equal to 3T half, the value of N0 becomes N0 by 8. And at 4T half, this is becomes N0 by 16. So this is the graph of time versus undecayed nuclei. Now what is the T half? T half is the time at which any radioactive sample decreases to its half. So from the radioactive graph we have n equal to n0 e to the power minus lambda t. So at t equal to t half, n becomes n0 by 2. So if we put n equal to n0 by 2, we can get n0 e to the power minus lambda, put t half in the place of small t. So we can get, that is e to the power lambda t half equal to 2. Take natural logarithm, that is e base a log. So this is comes to the first, that is lambda t half log e base a e equal to log e times 2. This e for taking the log, and this e is this present in the equation. Now log e base a e, log e is equal to 1. So we can get lambda t half into 1 is equal to log e base a 2. If we transfer it in log 10 base, then 2.3026 into log 2, that is 10 base a 2. So t half becomes, if this is ln2, this is the value of ln2. So if we put this value in calculator, we can get 0.693. 2.3036 into log 10 base 2 equal to 0.693 divided by lambda. So this is the relation between t half and lambda. Okay. This is the relation of t half and lambda. Now here if we take lambda equal to 1 by t, so if we take lambda equal to 1 by small t, then we can get n equal to n0 e to the power minus lambda into, put t equal to 1 by lambda, that is n0 by e. n0 e to the power minus 1 means n0 by e. Now n equal to n0 by e, if we take the value of NGE, that is N0 divided by 2.718, we can get 0.638 N0, that is 63.8% of N0. So from this we can write the definition of lambda or decay constant. So we can write that decay constant is reciprocal of time interval, because we put lambda equal to 1 by t. Decay constant is reciprocal of time interval in which, by at which time the radioactive nuclei becomes 1 by e times or 63.8% of its initial value. So we can get the relation between half-life and decay constant, and from this we can get the definition of decay constant. Now we can go with some numerical example. So in time t half, if half-life is t half, then N0 becomes N0 by 2, and 2t half, N0 by 2 becomes half of its value, that is N0 by 4, and after 3t half, N0 by 4 becomes N0 by 8. So if there are n number of half-lives elapsed, then the number of undecayed nuclei n equal to N0 half to the power small n, half to the power small n. Now small n is equal to t by t half, small n equal to t by t half. Now we go with this problem. Here we said that the half-life of radium is 6000 years, 1600 years, 1600 years. After how many years 25% of radium remains undecayed? That is, the value of n is N0 by 4, and we shall find out the time, not the half-lives, here time. So half-lives, number of half-lives equal to total time divided by t half. So total time equal to number of half-lives into t half. So from this equation we can find out at first t. So n equal to N0 by 4, therefore n equal to N0 by 4 equal to N0 half to the power small n. N0 N0 cancel, 1 by 4 equal to half to the power n, that is 1 by half square equal to half to the power n. As the base are equal, so the power will be must be equal, that is value of n equal to 2. Now total time t equal to number of half times, total time t equal to number of half times, that is 2 into half life is given 1600 years, that is 3200 years. So in this way we can find out the numericals of such types. We have go with the two equations here. So we shall go with the formula here is number 1, n is equal to N0 e to the power minus lambda t. Number 2, t half is equal to 0.693 divided by lambda. Number 3 is n equal to N0 half to the power small n, where small n is number of half-life, and number of half-lives, total time for decay is equal to number of half-lives multiplied by half-lives. So these four equations are very important to doing numerical example. One example we shall do. Please write down in your copy and try to understand and do other numericals. If you do not solve any numericals, please send to me or take the picture and comment me in my YouTube channel comment box. If you like my channel, please subscribe for new video. Next day we will go for some new interesting video about nuclear physics and also the class 11 chapter, that is motion in one dimensional, straight line on one dimensional motion and its numericals. Okay, so for today, thank you. Today is the video and thank you for watching my channel.